So should I go ahead and start?
Yeah, go ahead, please, Gabriel.
Okay. Welcome everybody to this tutorial session on reinforcement learning and optimal control and decision theory. I'm Gabriel Bernier-Colborn from the NRSC, if you don't know me. This tutorial is in two parts, so we'll be taking a break in about an hour for 15 minutes, and then we'll reconvene for the second part of the tutorial. If you have any questions, I think it's best that we use the chat feature in the Zoom, or you can use the Slack channel, and we have volunteers that will be relaying the questions to me, and I will ask the questions to Pierre-Luc. You can also raise your hand in the Zoom, and Xiaodan will be fielding those questions, so you might be able to unmute yourself and ask your question yourself. But you can, I think the chat function in Zoom is the easiest. We'll be taking time, well, I don't know how Pierre-Luc feels about this, but we thought we might keep the questions for the end of each half. But Pierre-Luc, if you want to take more regular breaks to field questions, that's up to you, if that's okay with you.
Yeah, I'm okay with that. I think
okay.
The only thing is if anyone is asking a question on the chat,
yeah.
I may not be able to see it, so perhaps Gabriel.
Yes. So the questions that are posed in the chat, I will ask to you. Okay. Same for Slack, and Xiaodan will be fielding people who raise their hands if they want to.
Sounds good.
So I'd like to welcome our presenter. We haven't spoken before, so I don't know if we pronounce your last name Bacon or Bacon.
Bacon in French.
Okay. This is Pierre-Luc Bacon from the Université de Montréal. Pierre-Luc Bacon is an assistant professor at University of Montreal's Department of Computer Science and Operational Research. He's also a member of MILA and IVADO at the University of Montreal. And he also holds a Facebook CFAR AI chair. He obtained his PhD at McGill and did a postdoc at Stanford. And his research is mainly focused on the problem of learning to take decisions over long time spans and its ramifications in optimization and representation learning. So Pierre-Luc, we're very happy to host you and that you took the time to do this tutorial. So if you're ready, you can take it away.
Sounds good. Thank you. So today the tutorial, I was trying to give you a sense of where reinforcement learning comes, and the thing about reinforcement learning is that it's inherently a multidisciplinary effort. And so in order to understand, to better appreciate how the algorithms came to be, it's important to realize that people sometimes have different goals, which shape the kind of solutions that they end up finding. And so to me, like, reinforcement learning is really the intersection of these three main fields, but it goes also way beyond into different sub-communities. But the kind of reinforcement learning that you would learn about in a textbook like Introduction to Reinforcement Learning is more inspired by the AI and computer science community, as well as people in neuroscience. So it's that circle up there. But of course, a lot of the tools and a lot of the foundations from the theory of reinforcement learning actually comes from optimal control, as well as in operations research. And interestingly, some of these tools have been developed and rediscovered independently. And there's also been some useful collaboration across fields, which led to new applications in each of these fields. So to give you like a really big picture of what these three fields are, I thought that it would be a good idea to summarize a little bit what's going on, but this is really a big picture. So I know that if you're a researcher in any of these fields, you might disagree with that big characterization, but of course it's just meant to give you the big picture here. And so in reinforcement learning, as saying, it's much more of a tradition rooted in AI, cog-sci, and neuroscience, and it's really about learning to act optimally. But the key word here is from interaction. So if you read the textbook by Intro to RL by Rich Sutton, there's going to be a lot of emphasis put on that word, interaction and experience. So it's that interactive process between a decision maker and its environment, which really is key here, and learning from experience. So in that sense, reinforcement learning is much more of a problem statement than it is a particular technique or algorithm, of course. So because of where RL comes from in AI, and because a lot of researchers have been attracted to AI with ideas such as AGI, coming up with AI that works in pretty much all circumstances. Typically, reinforcement learning tools, algorithms, and problem formulation assume very minimal problem structure. And it's meant to be that way because typically that black box nature is deemed to be a desirable thing. Now, in contrast, in optimal control, this is more of a tradition rooted in engineering communities where it's much more about trajectory optimization in nonlinear dynamical system. So when we talk about nonlinear dynamical system, it is naturally a concept which comes from a continuous time formulation. And so a lot of the applications in optimal control are concerned with things like aircraft, spacecraft control, robots. It's been used a bunch in all sorts of chemical process engineering, optimization, and economics, epidemiology, so on and so forth. So all these applications, they tend to be modeled as deterministic nonlinear dynamical system. But of course, there are more frameworks that have been used as well. And in optimal control, typically we tend to embrace a little bit more the problem structure. It's a bit more analytical. In the same way, in operations research, there's also more of a tradition of leveraging the problem structure to get the best solution possible for the given problem. And in OR, the difference is that it's been often concerned with problems such as supply chain management, policy modeling, transportation problems. So it gives a slightly different flavor to the algorithms and thought process when you read textbooks from that community. But the beautiful thing is that all these fields actually share the same tools, and they share the same mathematical foundations. And hopefully, I'll convince you today that it's a cool thing and that you should be looking across different fields to come up with new tools and new insights. And so this is a picture that you would have seen probably many times in a textbook on Intro to RL, but it's good to show again here, but with slightly different terminology that kind of spans across different fields. And so at the top of that picture, we have an agent, where agent is a term which we use more commonly in RL, whereas in optimal control, we usually talk about a controller. And then that controller, that agent, interacts with an environment or a dynamic system through some action or control. And so these actions can be discrete or continuous, but what they do is they affect the evolution of the dynamical system. And that environment, in turn, produces new states and outputs a reward or cost. So typically in reinforcement learning, we're concerned with maximizing some notion of reward, whereas in optimal control, it's often more in terms of cost. So the basic framework for many of these, for reinforcement learning and operations research is that of Markov decision processes, which is a formalism that was mostly developed in the 50s, starting from Bellman, Richard Bellman. And so an MDP allows us to formalize this agent interaction loop over there. And so it consists of a set of states, a notion of states, which state is the thing that allows you to express the evolution of the system. So it's all the information necessary to characterize the evolution of the system. And equipped with this, we also have a notion of action, which is the mean by which we influence the trajectory of the system. And how that action influences the system is described in terms of a transition probability function, And finally, the last component is that of a reward function, which importantly, and I highlighted this here, the reward function is an immediate quantity that quantifies the goodness of an action that the system takes in a given state. And immediate is really important here because we're not going to be optimizing for just a reward, but some function of the reward. And then you can mix and match and add other dimensions to that problem formulation. So you can have discrete or continuous time, discrete or continuous state, discrete or continuous actions. And you can have as well a finite or infinite horizon. So the horizon would be the number of steps over which you want to be taking decisions. So most of the time in RL, however, it's cast in the discrete time setting. But there are formalism as well for dealing with continuous time, which have mostly been used though in operations research. The continuous time formulation though is pretty standard in optimal control. So the goal that we're going to be pursuing is that of finding a policy, which is a way of choosing action in a given state, so as to maximize a given performance measure. And this performance measure, you can think of it as some sort of loss if we were to be in a supervised learning setting. Now, the thing is that we're not really going to be able to just swap a loss for another the way that it's relatively easy to do in, let's say, a deep learning setting where you just choose your loss and then the same algorithm holds. Here, the theory is going to be fundamentally affected by the assumptions that you make on that loss, so the performance measure. So there are a bunch of criteria that are defined that have been studied in the operations research literature. So oftentimes we deal with the total expected reward, the expected total discounted reward, average reward, and a bunch of other criteria that are a bit weirder. But most of the time in RL, we deal with the expected total discounted reward. So I think here I have a little demo. In fact, I should have shared with you. So I'm going to just switch screen. Let me see if I can do that. Can you see this here? So this is a Google Colab. And this was just a little demonstration to kind of highlight what this agent interaction loop looks like in practice. So if I can just run this thing here, I think I'm going to have to open it here. I think I'm going to have to switch account. Okay, I think we're back. Can you see this?
Yes, we see well.
Yeah, sounds good. That should work, I guess. Now, while the virtual machine is starting, just going to go back to my slide. So this agent interaction loop, the picture that we had a couple of slides ago, really described a process by which we're going to be generating and sample states and actions. So the way it works is that we're going to start from an initial state. From that state, we're going to be sampling some actions according to our policy. So I'm making some assumptions, by the way, on the kind of policies we're making here. I'm going to go back to this point in a few slides. But for now, we think of that policy simply as a conditional distribution of our actions, conditioned on the current state. And given that action, we can then compute the next reward. In this case, I'm assuming that it's a deterministic reward, but it's perfectly fine as well if you deal with distribution of our rewards. The framework is not going to be affected by that. But for simplicity, without loss of generality, we just assume that we have a deterministic mapping that takes a state in action and then outputs a new report. And then given the choice of actions that our agent picked, we can compute the next state by sampling according to a transition probability function. And then we'll repeat this these 4 steps for a fixed horizon t or for infinity. And that process will generate what we call trajectories. So this is how we induce some samples from the interaction of a policy with its environment. So let's go back to the collab here, just to highlight how these things work. So I'm going to be using a small synthetic example here. If you're interested, you can read the corresponding paper. It's a very interesting paper, but it's just chosen because it's small. It has 2 states, 2 actions, and we're just going to be playing with it. And so I create this environment, and note that this transition probability matrix function here has the property that when I sum over, let's say, the next state, I condition on a state in an action, and then I sum over the next state, this should sum up to 1. So this is a stochastic matrix, and that's what we're verifying here in that cell. Now, the interaction loop protocol, in a way, is expressed in this function here, which I wrote. It's a small generator in Python. So I have an initial distribution of a state. I pick my first state, and I feed that into my policy, which is a conditional probability distribution over an next action. Everything is discrete here, so it's a categorical distribution. And then I can already output the next state, the next action, and then we repeat. So then I can do this, and here it's written as a generator, so I can generate samples in an infinite number of times. And so this is what I'm doing here with this function called take sample. And let's see what it looks like here. So I've sampled the trajectory here of length 10, and this would be the sequence of rewards that I'm getting. And let me just switch again, go back to my slides. And remember that what we're interested in ultimately is to maximize some notion associated with the reward that our policy is going to induce in our process. And so we have trajectories here, and then we have corresponding rewards. So what do we do now? Well, we need to define that very important quantity, which we call the return. And I think this is something that if you're new to RL, it's very good that early on you try to disambiguate your terminology and really distinguish between reward and return. These things are very different. So the return is a function of the reward, and it's in our case it's always additive, and it's a sum of the rewards. So this is what we have up here. So we can take a simple sum like this, but we can also discount each of the individual reward. And why would you do that? Well, a couple of reasons. There's a modeling reason, first of all, that in some cases it might make sense to model the effect of rewards in a discounted fashion to basically express the fact that perhaps you care more about the present than the future. So this is what would happen if you set, let's say, gamma, the discount factor, to 0. Then in that case, basically you're completely myopic, and all you care about would be to maximize the current reward, because all the other terms over there will just disappear. Then in the same way, if we set gamma is equal to 1, then it means that we pretty much care about all the rewards in that trajectory. So this is the interpretation in terms of discounting, but there's another really interesting and useful interpretation in terms of a random horizon. So you can think of gamma also as defining a random horizon. So it's as if you weren't too sure about where the final time would be in your process, and you want to model that where t is now a random variable, specifically a random variable which is geometrically distributed. So it's as if at every step you were to flip a coin, and if it returns true, then you keep on sampling. If it returns false, then you terminate your sampling process. So mathematically, these two views are equivalent. And just to make this more concrete a little bit, let's go back to our notebook. And so what we're doing here is simply, I've defined a little widget here. Let's say we have a sequence of rewards. This is completely synthetic. I've just said, let's imagine we have 1, 2, 3 as rewards. And we say, what would be the return if our discount factor is 1? Well, it's easy. It's just a sum of them. So this is what we see here. Our slider is at 1. And then the rewards are 1, 2, 3. The discounts are all 1 for all of them. And so, so the discount return is just a sum. So it's 1 plus 2, 3 plus 3, 6. And same thing if we set discount to 0. Now this time, the only thing that we have, all the other terms go to 0, and then we're left with a return of 1. Then in between, we have intermediary values. So we go from 1 to basically all the sum of it. So this is a return from t is equal to 0, so starting from 1. But interestingly, there's a recursive structure here. So the return also at time 1 can be related to the return at time 0. And just to get a sense of how that works, let's once again set the discount factor to 1. In that case, just the sum of 2 and 3. So this means that the discount return is 5. Maybe I can zoom a little bit more here in case you don't see well on the screen. And then same thing, discount factor to 0, then, it's only the first term. And then finally, let's just continue our exercise and do that at t is equal to 2. So it means that now the only reward term that we take into account is the last term. So this is 3. So of course, if discount is 1, then the sum is 3. And in that case, also if we set gamma to 0, then it's also 3 because it's only one term. So now you might have kind of guessed that what's going on here is that if, let's say, things were to be discounted, undiscounted, so gamma is equal to 1, then what we've done in these steps, let's put the sliders back to 1 in all cases here. So what we've done essentially is to compute. We have here 6, 5, and 3. So what's going on here, we're basically computing the cumulative sum, right? So now you might wonder what's the equivalent concept when we introduce discounting? What's the equivalent of that cumulative sum when there's discounting? Well, turns out you can express these things in terms of convolution. Now, I'm not going to go into details of this, but I thought it'd be cool to mention because these are the kind of things that might be useful when you implement these reinforcement learning algorithms in some automatic differentiation frameworks, such as TensorFlow or PyTorch, or you name it, anything like this, where you really want to avoid having to code up like a for loop. So it is also possible to view this as a specific convolution, a recursive convolution. And this is just to convince you that it's true here, but I'm not going to go more into details of this. All right, so let's go back to the slides. All right, so this is the return, but the return is a random variable. And when we're going to be when we're going to be interested in finding optimal policies and working with the return, we're going to be working with its expectation. And so the expected return is going to be summarized into a function that we call the value function. This is what I write here, v pi of s. So v pi is the expectation of the return, but condition on the state. So it means that if you were to start your system in state s and run your system forward for, let's say, t time step or to infinity, and then compute the return, then this gives you the expectation, the expected return. And then it might be more obvious now as well as to the kind of restrictions we might want to put on the discount factor. So imagine if we're in the infinite horizon case here, that trajectory is going to be very long. And of course, if we want things to be bounded, we're going to want our discount factor to be strictly smaller than 1 so that we get bounded expected return as well. So the problem of finding the expected return associated with the policy in every possible start state is called the policy evaluation. And it's a very fundamental step to derive also other algorithms. But that policy evaluation problem is inherently a linear problem. It can be viewed as solving a linear system of equation. And so in closed form, you can compute this value function here as a solution to identity minus gamma p pi inverse times r pi. And these matrices, I defined them just below in that slide. So p pi is a matrix of number states by number states, where let's say you pick a row, this is your source state, and then the column is going to be your destination state. So if you sum over columns, that should sum up to 1. So this is just averaging, this is just marginalizing out the choice of action so that we go from this, let's say, multi-dimensional array, if we were to think in terms of NumPy, let's say, to a matrix. And then same goes with RPy, so we're just averaging out the actions so that we have a vector now. So this is just a linear system of equations. So we can code this up, and it's very much like what we have in the map here. So we form the PPy matrix, RPy matrix, and then we solve it. And just little tip here, I think that it's very cool to use this Einstein summation function. If you're not familiar with that, I highly encourage you to take a look. It's a very neat way to express what would be a messier computation that you have to express in NumPy. But here, this is essentially just computing that marginalization over there that we had on the previous slide. So you see, like, it's 3 lines, and then bam, we have exactly the true solution to the value function of our problem. We can test it here. There's not much to gain from like the specific values that are found here. It's just amounts to these values, but just to show you how simple that can be done. And then here internally, the solver in NumPy, I think, is using something like Gaussian elimination. So it's a direct method. Right, so this is the problem of policy evaluation, but ultimately we're really interested in finding good policies, so good ways of acting, where good is, of course, defined with respect to the performance measure that you've chosen. But for now, today in this tutorial, we're just going to be assuming the expected discounted return, which is the most common one used in reinforcement learning. And to be honest, I think this is probably for 2 reasons. First reason is that it comes with some simplification on the theory side, so it's much easier to use. And second reason might be also historical. We just started using it, and now we're kind of stuck with it. But yeah, we're going to be using expected return, but it's good to know expected discounted return, but it's good to know that other criteria also exist in case it might be a better choice for you to model your problem in a different way. So the problem we're interested in here is finding that optimal policy. And that notion of optimal policy is defined with respect to its value function. So this is how we're going to compare our policies with each other. We need to be able to say, like, which one is better than another one. And so that's why we're interested in finding a value of a policy. So this is what we have here, where we're maximized over the set of all possible policies. And then we're picking V star is the optimal value function. It's the one that is the highest according to a partial order of these value functions. And that partial order is component-wise. So it means that the V star is the vector with the property that in each of its components, it's greater or equal than any other vector in that set. So of course, that set of policies, big pi, can be very large. And so we might want to be a bit smarter in terms of how we solve that problem. We specifically don't want to enumerate all policies. So we're going to have 2 ways of dealing with this. So the problem is that we're going to, the first tool that we're going to use is that we're going to leverage problem structure a little bit. And that's why the discounted case is so, infinite discounted case is so useful, is that we can show without loss of optimality that it's okay to just consider stationary deterministic policies. So what that means, a stationary policy is a policy which has no dependence on the current time step. And so that is already pretty useful. And then the second thing that we can also show is that it's fine to just look at deterministic policies. So meaning policies that map directly from a state to an action. So meaning that we don't need to, let's say, have a distribution of our actions the way that I've written in the previous slide. And so that's going to help us a lot to reduce that search space in a way. And in order to avoid enumerating all the policies, then we're going to use a recursive property, basically based on Bellman's principle of optimality. And so that Bellman's principle of optimality, this is if you've taken classes in CS, this is exactly the same principle you would have seen in dynamic programming. So all that time, like studying for programming interviews, was not wasted time. It's actually the same concept. And in fact, myself, the more comfortable I became with MDPs, the more comfortable I also became at solving these CS puzzle questions, because now I can think of them in terms of MDP. And once it's written down in terms of an MDP, the solution is very simple. So,
Pierre-Luc, could you remind us what a MVP is?
Markov decision process.
Thank you.
So, just a reminder of that Bellman principle of optimality. If you remember, so what that statement basically says, so this is just me rephrasing it. It basically says that if a policy is optimal at a given state in time, then it also needs to be optimal in the subsequent states. So there's that recursive property about optimality. If it's optimal in the next step, then it's also got to be optimal in the if it's optimal in the current step, then it's also got to be optimal in the next step. So this is also the basis for, let's say, a shortest path algorithm, Dijkstra, and all of that. The same principle at play. And underneath all of that is there is a structure of an MDP hidden there. That being said, let's just put a little note here. Most of these problems in CS that we deal with are typically finite horizon MDPs. And in that setting, the existence of stationary policies is no longer the case. So we would have to deal with non-stationary policies, namely policies that depend on the current stage. Now, an important thing about this principle of optimality is that it gives rise to a set of nonlinear equations, which we call the Bellman optimality equation, which are written here. And so you see that there's a max in there, and that max actually has a big consequence in that it defines nonlinear equations. And nonlinear equations in general cannot be solved in closed form the way that we did for policy evaluation up here. So how are we going to solve this then? Well, if you've dealt with nonlinear equations previously, you might have seen a couple of techniques. And one of them is Newton's method, which we're going to see in the next slide. Or another one is if you have a fixed point operator, then you can use also the method of successive approximation to find a solution to your nonlinear equation. So if we apply the idea of successive approximation to the Bellman optimality equations from the previous slide, then we can show that we can find the optimal value function as a fixed point of the so-called Bellman optimality operator up there. So this operator, matcal T, if you were to write it in LaTeX, is an operator that takes an arbitrary vector and then computes this max over there. So if you're not familiar with operators, let me make this a bit more concrete. So I think when I started, that term like operator was thrown around a lot to me, and I was a CS student, so I hadn't really seen these tools previously. And the way that it clicked to me what these terms meant is really to think of it in terms of programming concepts. So I'll get to this in a second, but I just wanted to show you here in the demo that this is just a simple application of this idea of like what it means to have an optimal value function in terms of just listing out all of the possible policies and computing the corresponding value function. So this is what I'm doing here. Remember, we have two states, two actions. So we only have four possible policies, deterministic policies, stationary ones too. I'm just listing them all here. And then I can then compute the corresponding value function for all of them. And so by inspection, you can see that the first policy over there would be the one which gives us which would be optimal because it's larger than all of the other value functions, which I've stacked as rows here. And then so first policy here is would be an optimal policy. So this policy in particular is the one that picks action 0 in state 0 and action 0 in state 1. Okay, so let's now just convince ourselves that this idea of applying the successive approximation method is sound. And I had just started telling you like what this meant, this operator. So this operator, you think of it as a function that takes a function and produces a new function. So literally, that's what I'm doing here. I create this little closure function, which is I call Bellman operator. And what Bellman operator does, it takes a vector, computes that mapping, and then returns a new vector. So it's not quite like exact equivalent in terms of functional programming. We'd have to like pass a function, return a function. Here I pass a vector, return a vector, but it's pretty close to the same thing, right? So that's all it means. This is the Bellman operator, and then what the method of successive approximation consists of is you start with a guess on your solution, then you keep on applying the operator, and then if your operator is a so-called contraction mapping, you can show that the contraction that you're going to be able to find a unique, there will be a unique solution, and you're going to be able to find it as a result of applying that successive approximation method. So you start with a guess, feed it in the Bellman operator, that gives you another vector, and you keep on repeating, put it as input, output until convergence. So here I'm just running it for 50 iterations. But if you remember from our example, this was a value function associated with an optimal policy. So by the way, there could be multiple optimal policies, but there exists only one single unique optimal value function. So this is something like 0.16 and 1.89. It's basically where that thing is going. If you were to just let it run a little bit more, you'd approach it. All right. So the idea of applying the Bellman operator and combine that with successive approximation in dynamic programming in RL, we call that value iteration. But it's good to know that there's a more general pattern behind this. And just as a side note, instead of using a max here, you might also want to use a smooch, a soft maximum, aka like a log sum x, for example. And the reason you would want to do this, and I think we'll get to this towards the end of the tutorial, is that in some cases, it's useful to guarantee some differentiable property. And it's one way in which you can ensure that. So this is something that was introduced in Rust 1988, but it's been rediscovered also in the context of inverse RL, and more recently in the context of soft Q learning. So simple thing, you take the Bellman optimality operator and then replace the max with a log sum x, and replace the argmax with soft max. Okay, so the first approach for solving that nonlinear equation was to use the method of successive approximation, but another really commonly used tool in solving nonlinear equation is to use Newton's method. So it can be shown, and that was shown by Puderman and Brumel in 1979, that basically applying Newton's method here to our problem is equivalent to an algorithm that we call policy iteration. And a side note here, Puderman is a Canadian researcher who's from the OR community and made a very important contribution in the field. He's got a textbook which I've read many times and is always a reference that I probably read almost every week. So Puderman 94, so a researcher at UBC, and Brumel. And I think that result as well was probably described while Puderman and Brumel were at UBC. And so Newton's method corresponds to policy iteration. And what that policy iteration algorithm is now instead we're going to start with a guess on an optimal policy. We're going to compute its value function. And then we're going to improve locally that policy by computing this argmax over there based on our current guess of the value on the actual value function of that policy. And then we're going to keep on alternating these two steps. So let's check and see what that looks like in terms of code. So now instead the body of our for loop is consists of two lines. First line we call our policy evaluation method. And the second line, we simply take that vpi that we've computed for our current policy, and then we compute the new improved policy by taking the argmax. Sometimes in RL, we call that step the greedification step, because the policy that we get out of this value function is greedy. It's greedy with respect to the choice of action. But of course, it's not greedy with respect to the immediate reward function, but it's greedy with respect to its values. So let's run this, and we see that conversion is much faster. And maybe it's not surprising when you think of this, because this is essentially a second order method in the sense that it looks like it's pretty much like a Newton's method. So policy iteration is also a pretty efficient algorithm, tiny bit more expensive though, because we need to do a policy evaluation at potentially every step. Any question here?
I would actually have a question. Here we see that the value function is not changing, but the policy is, since it has not reached the terminus, right?
That's right. So the termination criteria for policy iteration is you can show that in finite, in the discrete case, whenever you're going to encounter the same policy twice, it's going to mean that you've converged. You can stop policy iteration once you've found the same policy twice.
In practice, is it important to find the optimal policy, or just finding the optimal value function is sufficient?
So so you get both at the same time, right? Because you compute the value function corresponding to your policy, and then you output the policy at the same time. So you get both at the same time. Okay. If the question is regarding the termination criteria, there exists a lot of criteria to stop, especially for value iteration. I've kind of implied in the previous slide that you do this process for until infinity, but actually there are bounds that allows us to better control when we stop, and these bounds are very much used in OR. That being said, they're not like really thought that much when you read RL textbooks and you come more from the CS side of things. So it's also good to know that there are good bounds that you can use to make your algorithm more efficient and terminate appropriately.
Interesting.
Yeah, please ask me questions, because I'm kind of losing my voice, so it's good if.
Yeah, sure. By the way, Pierre-Luc, we're going to be coming up to the break in about 15 minutes. So if you find a natural sort of stopping point, or if you just want to have a glass of water, just tell us.
Sounds good. I think the logical break point is going to be after this section on approximate dynamic programming.
Okay.
So the next logical extension to what we've seen, which, by the way, we would refer to as dynamic programming, typically in reinforcement learning, is approximate dynamic programming. So as you have seen in the previous slide, in a way, like you require a lot of knowledge about your system. You need to be able to know what's the transition matrix, what the reward function, and if you're dealing with very large system, you might have also a very large number of actions and very large number of states. So approximate dynamic programming is really about trying to address the problem of dealing with large set of states and actions, and also it also deals with the fact that when there are cases where all you would have access to would be, let's say, samples of the MDP, and that could be for two reasons. Could be that you just don't know the MDP, or that the MDP is so large that there's actually no way to express it tractably in terms of, let's say, a multidimensional array in your computer. So this is a paradigm that allows us to deal with these issues. And the issue of not knowing the true like P or R and only working from sample is often referred to as simulation-based approximate dynamic programming. And this is a terminology that you would encounter when you read the textbooks from the OR side, but not the RL side. And maybe the reason is that in RL, we like to pretend that what we do that is applying RL to the real world in a way, right? When we when we apply our algorithms in our environment, we just pretend that it's not necessarily a simulator, but that we're just mimicking the real life. And so there's less of that notion of a simulator. But if you take a more pragmatic point of view on what these methods are doing, and put your OR hat, then you would call that a simulation-based ADP. So what we're going to do here is instead we're going to be parameterizing the value function, and we're going to be trying to find an approximation to the value function. So let's say we're doing linear function approximation. What it means is we're going to be interested in finding a set of weights W, such that when I take the inner product of a feature vector phi in W, that this thing's going to be close to the true value. And then you can cast that as a essentially least square problem, where you want to minimize the weighted L2 norm between your approximate value function V hat and the true value function V pi. And please keep in mind here that what we're doing is policy evaluation. We're not trying to find an optimal policy here in the next few slides. We're just saying you pick a policy, pick your favorite policy pi, and then our goal is to compute its value function. But in this case, we're going to be doing it without knowing the model. So it's going to be model-free reinforcement learning. And what makes this problem hard, because you might see this argument over there and like, well, this is just linear regression. So where's the issue? Well, the problem is that V pi, we don't know that V pi. This is the thing we're trying to estimate. And so as opposed to a typical linear regression setup, we don't have access to the true target. We don't have access to the labels. And so we have to come up with a way of kind of creating our own labels. And then similarly, also, we can't form that matrix big phi, which would be just kind of a conceptual matrix of the number of states times the number of features, which is way too large to fit in memory. So we need to come up with a solution to that. So that solution is going to be based on a generalization of what I like to call the policy evaluation equations. So this is usually called the projected Bellman equations, but I actually prefer to call that the projected policy evaluation equations. The reason is, if you see the expression Bellman equations outside of RL, it always refers to the optimality equation, not the ones associated with value function approximation. And so nevertheless, let's call that projected Bellman equation. So the difference here is that we have this projection operator big pi here in terms of this other linear term over there. And so we're trying to find a solution V hat pi such that these two sides are equal to each other. And this is a linear problem, by the way. So if we were to set big pi to identity, then would fall back to just a simple policy evaluation case, which is just an iterative algorithm for finding the value function associated with the policy when you know everything. So from an operator theoretic point of view, this projected Bellman equations can also be seen as the composition of two operators, one of them being a big pi here, a projection operator, and the policy evaluation operator, Markov T. So it's useful to visualize these things geometrically. And this is a picture you might have seen already. So here we just presume that, let's say, the space of value function that we can represent is that plane over there. So this is the set of basically all possible weight vector W. And this would be the space that it spans. And then what we do is whenever we apply our policy evaluation operator, that brings us to a point which may not be representable in the space, that plane over there. And so what the projected Bellman equation operator does is that it projects this point back onto the representable space here. So this is the composition big pi Markov T. And this is the new point over there. Now, on the side here, I drew, I imagine that the true value function would lie outside of that space. And then this would be its orthogonal projection in the representable space. Now, everything on this picture kind of assumes that things are orthogonal, and it's really a picture that you'd visualize in normal Euclidean space, but it's a bit more subtle than that, because actually what's going on, and I think this picture is a bit misleading when you see it for first time, because what's going on is in fact that this big pi, and I'll show you details in the next slide, that big pi corresponds to an oblique projection. And it's an oblique projection is just a generalization of an orthogonal projection, which is defined by a pair of two subspaces, where one subspace defines a plane to which our projection is orthogonal to. So this is the little square here, so showing that this vector is orthogonal to that plane here. And then we have the usual orthogonal projection. So what we're doing in the policy evaluation projected Bellman equations, pardon me, is more akin to applying an oblique projection. And as you can see, depending on the angle of that plane, we may get further away from the true orthogonal projection. And for that reason, there's going to be some bias introduced depending on the kind of oblique projection that we compute. So let's be more precise about the form of this projection, the form of big pi. So we can show that the so-called class of LSTD lambda, which is an approach to approximate dynamic programming, the solution to this algorithm is can be found as the solution to the linear system, where we have a matrix A lambda and B lambda, which are of this form. And I think that what's useful to see is to just pretend, let's say, that lambda is equal to 1. Because, by the way, lambda is going to vary from 0 to 1. So let's think about setting lambda is equal to 1. Then you see that in matrix A, the first two terms will cancel out. So it's going to be identity. And then it means that the solution is going to be of this formula there. And this is essentially a hat matrix. If you remember from linear regression or general least square, this is what the hat matrix would be, but where v pi would be given. So this would be, let's say, your target, and this is how you do linear regression typically, except that here it's weighted, and that z term is a diagonal matrix which contains the stationary probabilities for the current policy pi. And this is very important that it matches the distribution of pi, namely that it's on policy. Because if it's off policy, then that matrix A inverse may not exist. So this was more the
Pierre-Luc, could I interrupt? We have a question from Chris, who asks, is that oblique because the basis functions are not orthogonal to each other?
No, it's oblique because we introduced these additional terms over there, and I'll get to this maybe in the next slide. But this term here is connected to the so-called eligibility traces in reinforcement learning. And essentially, we're defining an oblique projection instead of an orthogonal one. And you can also think of this in terms of matrix preconditioning. So what's going to happen too, as you set lambda is equal to 1, you're also going to increase the convergence rate. So it's going to be faster, but it comes also at a cost, which is variance. And we'll see that, I guess, in the next slide.
Thank you.
Does that answer your question?
I assume it does.
So this was the analytical point of view on LSTD, but of course LSTD is a model-free approach, so we're not going to be computing these matrices. We don't know P, right? So we can't express big phi. So we can show, and that I'm going to be a bit hand-wavy here, but the gist of it is you can see these matrices, turn them into expectation, and then basically estimate all these terms from data. So you sample a long trajectory of n samples, and you compute these matrices. So this is going to be an outer product. So you're going to get a matrix and a vector. And that z term here is a so-called eligibility trace. And the eligibility trace is really like in AI / psychology / neuro concept. As far as I know, it's due to Sutton, who himself was very much influenced by the work of Harry Clough in 1972 on the hedonistic neuron. So these eligibility traces were introduced as a way to model the decaying effect of memory in neurons. And I think this is my own historical interpretation that Sutton and Bartow in the 80s were interested in bringing up these things more in terms of modeling tools. And just later on, that beautiful connection to oblique projection and then all the properties that it brings were understood much later on. So it was not a choice that was made like on purpose. All these connections and interpretations were added later on. And in fact, the oblique view is something relatively new that has been introduced by Bertzikis in around maybe 2010. So this LG trace can be defined in this way, in an offline manner, but also it lends itself to this very nice recursive online implementation, which was more the basis of what Sutton and Bartow did back then. So this algorithm called LSTD lambda was introduced by Radke and Bartow in '96, and then studied by Boyan, extended by Bertzikis, and then studied again by Janie Roux in 2010. So it's a pretty efficient algorithm, one which is quite popular on the OR side, but a little bit less in the AI / CS reinforcement learning side, because you need to be forming these matrices over there, and depending on which camp you are, this may not be something you want to do, because it involves in square operations, plus you need to be solving a linear system here, which if you use, let's say, a direct method would be order and cube. So because of computation cost and a little bit more memory, this might not be desirable. And so the alternative that is often used in the RL side, AI side of things, is to use so-called temporal difference learning, which was introduced by Sutton in the 80s as well. So his thesis was in '84, and then there's this 1988 journal paper on TD. So temporal difference learning, very high level, can be seen as a stochastic approximation approach to policy evaluation. And by casting this as a stochastic approximation algorithm, what it buys us is that now we have linear time complexity in memory. But also a drawback, and this was studied a bit more carefully by Janie Roux, I presume in 2010, is also tends to be less sample efficient. But we gain a lot in terms of speed. So what we do instead is that we form a sequence of iterates where, same as usual, we parameterize your value function by a set of weights. And for generality here, I assume that the value function might also be parameterized by a nonlinear function approximator, for example, a neural net. And what TD does is that it computes this so-called TD error, which is kind of creating a fake target for the target that we don't have, because we're not doing supervised learning. So it's creating this guess, and it's making a guess from a guess. So it takes the current reward you got, then it adds the estimated return from the next state minus its previous guess. And this defines a scalar, which we call the TD error. Then we multiply the gradient with respect to our weights of the value function, and we modulate that by the TD error. So if we use linear function approximator, then this derivative is simply the feature vector. And this algorithm here is called TD0. Called TD0 because the 0 parameter here refers to the lambda parameter. And the same way that we have eligibility traces in LSTD, we also have eligibility traces in temporal difference learning. Now the catch here is that if you use nonlinear function approximation, this algorithm may not converge. And you can find a counterexample in this paper by Tsitsitis and Benjamin Van Roy in 1997 that shows this very neatly. And if you're interested in the mathematical details, let's just tell you that the big picture is that this function composition big pi times matcal is such that we have a non-expansion, and the non-expansive property may not be guaranteed when you have nonlinear function approximation. Nevertheless, it's been used quite a bunch, nonlinear function approximation, and actually way earlier than we think. So DPRL is, in a way, been studied a while ago, starting from Tesoro in 1992, which is often credited for being able to show for first time that TD could be used at scale with nonlinear function approximation. That was in the game, the backgammon game. And so what Tesoro did is use neural net to learn the values. So in particular, the state action value function. So this is just the expected return, but conditioned on the state in action. And then in order to find an optimal policy, so here we're no longer just in the policy evaluation regime, but in the problem setting where we also want to find an optimal policy. And so in order to get an optimal policy in that kind of scheme, what you do is that you keep on changing your policy slowly by doing dithering, by injecting a little bit of noise and wiggling around. So that wiggling is achieved by having an E-soft policy. And what that means, for example, is you can pick a Boltzmann policy with temperature tau, and then you feed the current Q values in there, and then you sample actions according to this. So you're kind of sampling around your current action, so you're not totally greedy. And then that kind of exploration mechanism is what allows this algorithm to work. So this is called nonlinear SARSA, but the gist of it is that it's simply applying the TD rule, but now to estimate state action values, and then doing that dithering, that wiggling around Q to find an optimal policy.
Pierre-Luc, do you think now would be a good time for a break?
Let's me say this one thing,
sure,
and I think we'll be good. So the related algorithm to SARSA in the nonlinear case as well is called Q-learning. It's the one that you might have heard the most about. So Q-learning is also a stochastic approximation algorithm that allows us to find a solution, an approximate solution to the Bellman optimality operator. And I keep mentioning these stochastic approximation algorithms, but what they are really a stochastic approximation algorithms. They're algorithms that allows us to find zeros of a function, but only from samples. And that's why actually these algorithms are possible in RL, right? We had the template for stochastic approximation comes from Robbins-Monroe in the 50s. And what the zero problem is here is that we want to have the two sides of the Bellman optimality equation to be equal to each other. So we can write it as zero. So when you apply stochastic approximation to this problem, you get an algorithm called Q-learning, which is very much like TD. In fact, it is temporal difference learning at the core of it. But instead, here we form an update target in a different way, and we'll have this max operator in there. And what's special about this algorithm is that the max over A, this A that you pick here, the maximum, might not be the A that you actually use in practice. So it's an algorithm that is off policy. It allows you to learn about a behavior which is not the one you're currently following. And this is in contrast with SARSA. So we'll just stop here. And then once we return, we'll continue with this, see how it connects with fitted value methods. And then we're going to talk about policy gradient methods. I'm going to say a few things about optimal control in model-based RL, and that should be it.
Great. So everybody will be taking a 15-minute break. So since it's 2:35 Eastern, we'll come back at 2:50 Eastern, so in 15 minutes. Pierre-Luc, are you there? Okay. I don't hear you. You might be on mute at the moment.
Yeah.
There we go. Everybody, we're going to start back up again. We're going until 4 o'clock today, unless Pierre-Luc finishes early. Again, if you have any questions you want to ask, you can ask them in the Zoom chat function, or in French it says converser. You can ask them on the Slack channel as well in the channel for this tutorial. Before we start again, I have a couple of people who have asked if your Colab notebook will be available online, Pierre-Luc?
Yeah, that was the goal. I just didn't have time to click the chat. I can try to do it right now. If you give me 1 second.
Yeah, sure.
Collab here. And I had... you want the link in view? I think this is good.
So if you could copy that into the chat.
In the Zoom, yeah, group chat.
Perfect, and I'll copy that in the Slack channel as well.
Yeah, can someone try to just open it, see if the permissions are correct?
Sure, I'll try.
It's good?
Yep.
All right.
So you can go ahead and start.
Yeah, so I think there might be one more thing in the notebook, but it's mostly done for now. There would have been so many things I would have liked to demo for you, but I think we would have needed like a day or so. Unfortunately, I had to stop there. I have more notebooks that I might be able to share later on if you follow me on my Twitter or something, or maybe on my webpage, because a lot of these slides and examples were taken from my class that I'm offering at Milan, University of Montreal. So yeah.
Great. I'll post your, is it okay with you if I post your personal website on our Slack channel?
Absolutely.
Great.
All right, so just before the break, I said, I talked about Q-learning, and we just looked at this update rule over there. So this is like an update rule that looks pretty much like TD, except that technically speaking, what's happening now is that our Markov chain is over state action pairs instead of only states, but that's just the same thing. Second thing we're doing is that we've substituted this max operator in there. And by doing this, now we have an algorithm that is trying to find the optimal value function, the optimal state action value function, from which we can derive an optimal policy. And the interesting thing about this algorithm is that it's inherently off policy. So I think someone would have to mute their mic. Gabriel, you can just have a look.
Yeah, I'm looking for it.
This max operator in there. And by doing this, now we have an algorithm that's trying to... Thank you. So it's an off-policy learning, meaning that the actions that are chosen in that max over there may not be the actions that you actually experience in your sampling process. So this is a good feature. It means that it's more robust and you can choose a different policy. So you might have seen this algorithm in a deep learning setting, and it's often introduced by saying that basically Q-learning is minimizing the L2, some L2 distance somewhere. So it's like an L2 loss. It is true, but I would like to just make a point here that once again, these algorithms, temporal difference learning algorithms, are not stochastic gradient algorithms. Even though you might be using some gradients and you might be using TensorFlow to implement this, the resulting algorithm is not following the descent direction that would correspond to the true gradient, which we don't have access to. And the reason why we're tempted into thinking that it's only doing L2 minimization, some sort of regression problem, is that you can express the update rule of Q-learning by coding up an L2 loss in your framework. Because if you have a function of the form some scalar minus a function b of w, and you take the gradient with respect to w, then you get a minus b times the gradient of b with respect to w. And that's essentially the form that we have up there. So you might think, well, this is just L2. This is just a typical supervised learning setup, but not quite. And the reason is that this A term is not just a constant. It's a function that depends on W. So if you do that naively, and you take the gradient, then it's not true you're going to get this update rule. So what you would do usually when you implement these things is to put some sort of stop gradient around A so that you don't take the gradient in A and you view A as a constant and not a function. And why that problem occurs, once again, is because unlike supervised learning, the target itself depends on the weight because we're making a guess about a guess. This is what we call bootstrapping in reinforcement learning. So if there's something that you should maybe remember out of this tutorial is that value-based methods like temporal difference learning are not stochastic gradient descent algorithm. Now, you might see this update rule of Q-learning as basically an extreme approach on the stochastic approximation spectrum within the family of so-called fitted value methods, which were introduced by Jeff Gordon in 1995, where what we're trying to do, once again, is to kind of balance out the two sides of the Bellman optimality equation. But now we view this really much more like a supervised learning problem, but where we're trying to balance out the two sides by taking a loss, which is now the L2 between the two sides of the operator, and by basically minimizing over this expectation where the distribution is over state action pair under the distribution of samples that is generated by your current policy. So if I were to give you a fixed W bar, that would amount to just a regression problem. And if you have a regression problem of that form, you might apply a bunch of different tools, especially if you were born before the deep learning revolution, let's put this way, of the last year. You might have thrown some other function approximators other than neural net, and in particular, this approach, the fitted value methods, in which you use extremely randomized trees, is an approach that was introduced by Damien Ernst in 2005 called fitted Q iteration, and it's been a pretty successful approach and one that still works pretty well. I would actually advise you to try it out as well beside your neural network. So what we do, we just fit like an extremely randomized tree. You can use scikit-learn to do that. Or in fact, any linear regression, not linear, but any regression method in, let's say, scikit-learn to minimize this kind of loss over there, which is a proxy for finding an approximate Bellman optimality operator. Now, if you do that minimization here, and where you use Q, where Q is represented as a neural network, and you use stochastic gradient descent to minimize that loss, that gives you an algorithm called neural fitted Q iteration, introduced by Martin Brandmiller in 2009. And interestingly, as we'll see in the next slide, neural fitted Q iteration is really the precursor to DQN. And the advantage with this class of fitted value methods is that they're inherently offline, and they lend themselves very well to dealing with batch data. So if you can't gather data interactively, which is typical of healthcare application, education applications, and tutoring systems, or when, let's say, you're trying to design a policy that you don't want to deploy. Can you still hear me?
Yep.
Okay, so I think I've hit some cables. Just a second. Great. Okay, I'm back. Can you hear me?
Yep.
All right. So neural fitted Q iteration is really the precursor to DQN in 2015 at Google DeepMind. So what DQN is essentially is a fitted value method. So it's neural fitted Q iteration where you use stochastic gradient descent instead of batch gradient descent, and in which you instead of taking only one fixed data set of samples, you keep on gathering new samples interactively. So it means that you get new policy, get new fresh data, and then keep on refitting your Bellman operator. And so the reuse of samples is called experience replay. It's due to Lin in 1993, and that's pretty much it. And in fact, this concept of target network in DQN is nothing but this W bar in this expression for fitted value methods. So it's an old idea, but one that was executed very well. And DQN spurred a lot of interest in the combination of deep neural networks with reinforcement learning. So it's been an important milestone in the field, despite that the ingredients were pretty much there already, but they've been combined in a way that had led to some impressive results for the time. Okay, so all the methods we've seen so far to find policies are based on deriving an estimate of the Q values for a policy and then improving that policy based on our value function. There's another class of method which I very much like that we commonly refer to as policy grading methods in reinforcement learning. And the idea is that instead of trying to find an approximate solution to the Bellman optimality operator, what we're going to do is that we're going to be parameterizing the policy directly. And then we're going to be trying to adjust the parameters of our policy such that it maximizes the given objective. And as usual, we're going to work with the discounted, infinite horizon discounted case. So this is the expression over there, J of theta. This is our objective. And here it's not conditioned on any state because we assume that there's an initial distribution of our states. And I wrote expectation sub theta to highlight the fact that the dependence on theta is through the distribution of samples that is generated by our current set of parameters.
Pierre-Luc, can I interrupt a second?
Yeah.
Chris Drummond would like to ask, doesn't the past data become progressively less useful as you train?
In the experience replay buffer in DQN?
Yes.
Yeah, so there's been various add-ons that were developed based on this. One follow-up on DQN that was pretty successful was called the prioritized experience replay, in which data that's basically more relevant to you is replayed more often. So there's that weighting mechanism.
So it's a sort of a curriculum learning sort of.
In a sense, a prioritization, a reweighting of the data so that more useful data gets used more often.
Okay, thank you.
The intuition is right. And yeah, if you have the ability, by the way, to gather new data, then you should definitely do so. It makes a big difference, at least from experience too. If you're giving a fixed batch of data, yes, in practice, you can keep on refitting your approximate Bellman operator, but there's a limit at which you can extract information out of it. So if you can gather more data, then it's definitely going to be useful. Sounds good. So pi sub theta, this is our notation to denote a policy parameterized by theta, and that pi has to be stochastic. This is an assumption we make for differentiability reasons. The big pattern behind, the big picture behind policy grading methods and the ingredients really come from derivative estimation, which is studied a lot in simulation, in the simulation community. Now, of course, these tools in reinforcement learning have been developed independently from the results and the knowledge from the simulation community. But I'd like to give you a little sense of how these things connect. And that connection has been acknowledged a bit more recently. And I think we have a lot to gain also on learning more about the tools and the results that were derived in that field, actually starting from the 90s. There's a lot of knowledge about this. So the big picture and why derivative estimation is needed and why it's difficult is that we're trying to find the gradient of some objective, but that objective is an expectation. We can't compute that expectation tractably too, because we might not know what is the underlying distribution, or because it's just too large. The set of all possible, let's say, action state is too large. So all we want to do is take the gradient of expectation, which depends, whose distribution depends on theta, and where the stuff inside depends on theta too. And why this is difficult is because the dependence here is what we call a distributional dependence on theta. It's distributional because the underlying probability density function P sub theta depends on theta. So this is what we have down here, where I just wrote the integral explicitly to highlight the fact that the distribution of samples depend on theta. And because of that, when you push the gradient in, assuming that you can do it under some technical condition, you can push the gradient inside, then by the product rule of calculus, you're going to have two parts. The two parts, the first part is all good because you can write it back as an expectation. The problem is with the second one. And the problem here is that this is no longer an expectation, right? You see here we have P sub theta, but here there's no such thing anymore. We have now the gradient of P theta, and this thing here is no longer a probability measure. And why we care about having an expectation is because we want to be using Monte Carlo integration to estimate that thing. We want to get an estimate of our gradient by just drawing sample from an expectation. Because otherwise, what could you do? Well, let's say if you were to know maybe P, then you could perhaps do a numerical integration with quadrature rules. But in the problem setting that we're interested in, these things are not feasible. So the only feasible thing is to do Monte Carlo integration. So how you do this? So we're going to transform this second integral into an expectation by essentially applying a change of measure, aka importance sampling. So in importance sampling, what we do is essentially just reweight the terms inside the expectation so that now the density can be expressed in terms of Q. Q is a new density. And then we can show that the gradient of J is exactly equivalent to this expectation, but where now we draw from Q instead of P sub theta. And what we've done is that now we've re-expressed the second term fully in terms of an expectation. So this idea is known as the likelihood ratio estimator in the simulation community. And it's credited to some Russian researchers, Alexandrov and colleagues in 1968. And if you set Q of X to P theta X, then of course the first term, the first importance sampling weight goes to 1. And then in the second term, we get P theta X. Then the resulting estimator that you get is called the score function estimator and been studied a lot by Rubinstein in the 80s. And this is the basis for the so-called reinforced estimator introduced by Williams in reinforcement learning in 1982. And as far as I know, this has been introduced independently of the prior results from the simulation community. So you would have, if you've heard about reinforced, you've probably seen an expression involving a log term. And where is that log term coming from? Well, it simply comes from the fact that when you have that ratio here of the gradient of P over P, well, this is just by basic calculus, this is just equal to the gradient of the log of pi theta, which is equal to 1 over pi theta times gradient of pi theta. And that's it. So really, if there's something to remember out of this, is that the reinforced estimator at the core is an application of importance sampling. And the log in there, although there's a lot of emphasis that is often put in tutorials around the log bit is just sugar coating on an expression. It's simply expressing the same thing using calculus, but it's just hiding underneath what would be otherwise an importance sampling ratio. So if you apply the score function estimator, where H would be the return, X would be the trajectories, and theta the parameters of your policy, then you get the so-called reinforced estimator of this form, where we have the sum of the rewards, but this is now weighted by the sum of all the gradients starting from the beginning up to now. And in 92, Williams gave the interpretation of that term over there in terms of a trace, an eligibility trace that we discussed earlier. So it was just a reinterpretation because it's something you can update recursively. But this is not exactly the form that we use nowadays, because you can show just by reordering the indices on the summation that this is just equal to, instead a sum from t is equal to 0 up to big T, the end of your trajectory, of the gradient of a log policy times the return from that point on. See, k here starts at t, the current time step, so it's the return. The reason we prefer this expression is that the previous form involves accumulating gradients on the side, which for neural networks would not be a very feasible thing, where we'd have to basically keep a second copy of our networks, keep on updating it, whereas this is a perfectly equivalent form, but where all we have to compute are sums over rewards, and that gradient over there need not be expressed explicitly in our code, because we can code up a so-called surrogate loss such that if we take the gradient of that surrogate loss, it's going to give us the same as the stuff inside here. And that surrogate loss is simply the log of your policy times the return. So it's kind of a cross entropy loss, basically a weighted cross entropy loss. So this is what I'm saying here, that you can just code up this surrogate function. So I think these two lines should be switched actually, because there's no graph here. There you go. And maybe something to keep in mind again is that reinforce is not, the surrogate loss is just a trick to implement the right gradient. Namely that ultimately what we're doing is to maximize return, and we're not really minimizing that surrogate loss. That surrogate loss is only there to help us form a gradient estimator. And just to recap again, why we need a gradient estimator, it's because we have a distributional dependence on the parameters, something that would not happen in a typical supervised learning scenario, where the dependence of samples does not depend on the parameters of your neural network. So this is why we don't have to care about these things usually in supervised learning, where we're training deep neural networks to predict labels. It's really because we have distributional parameters. If you apply reinforce just like this, you would quickly find that it has a lot of variance. So what we do oftentimes is to apply a variance reduction technique known as controlled variates in the simulation community. And what a controlled variate is this other random variable, which is correlated with the thing you care about. And so in RL, we call that usually a baseline. This is terminology that Williams introduced in 1992. And you can show that in this form here, this gradient estimator, you can introduce any function that depends on the state only, and that is not going to introduce any bias in the resulting estimator. However, it might help you reduce the variance a lot. And so typically what we're going to choose for a baseline would be some estimate of the value function, but there could be a lot of other control variables that are chosen. So I encourage you to look at the paper by Schulman in 2015 on the so-called generalized advantage estimation, generalized advantage estimator. So these are pretty useful in practice. They work very well, and it makes a big difference. So no worries if you just apply reinforce out of the box and you don't get good results. Try it with a baseline. It's going to probably change a lot of things. Now, if instead you start this derivation in the infinite horizon case, and we forget for a second about this likelihood ratio trick, you can also rederive a similar expression. And this is the result that was shown by Sutton and colleagues in 1999. This is a typo here. It should be 1999, not 1992. And the result, basically, it starts from the objective, where this is the closed form expression for the expected infinite horizon discounted case. And this alpha vector is just a distribution over initial states. So if you work out analytically the gradient of this expression in closed form, you can re-express it in a way that looks like this, where we have the gradient of the policy times the Q function. And this business here about 1 minus gamma has to do with the fact that this matrix identity minus gamma pi inverse times the initial distribution does not define a proper probability distribution over states. So you need to do that reweighting business here at 1 over 1 minus gamma. But let's not focus too much about this. but more that this expression over there involves a Q function, and that Q function is something you don't know. So if you want to implement that gradient estimator, then you need to maintain a Q function on the side. So the idea of maintaining a Q function on the side in order to get gradient estimates is the basis for the so-called actor-critic architecture. I'll show you a picture in a second. The thing I wanted to say here, and I think I have a Colab notebook for you, is that you can actually compute the true analytical gradient in closed form with a tool like JAX that allows you to take gradient through a linear solver. And I think this is pretty cool when you want to debug your code, because you can get the true solution and then see if your gradient estimator makes sense. At the core of the derivation in Sutton and colleagues is really the application of the implicit function theorem. So it's not written in that form, but this is how I like to teach it in my course, at least, because of the recursive structure from the policy evaluation equation. You can view it in the framework of implicit differentiation, for which I'm going to say maybe one more sentence towards the end. So let's just go back to the notebook, and this is the last. Should be the last cell. So it's kind of amazing that you can use a tool like JAX, which if you haven't checked this out yet, you should. It's really, really neat. So what I'm doing is literally writing down this objective as if it's written in math. So I do policy evaluation to get the value function. So this is going to be the identity minus gamma p pi inverse times r pi. This is what I get. And then I just take the dot product with the initial distribution. That's it. And then that gives me a scalar. And then I call grad on this function. And then let's see, well, what's happening here is I'm just plotting the iterates of gradient descent. And I know for this example that the optimal value function is something like 1.0272727. So it's kind of going the right way.
So grad is provided by JAX here, right? So
yes.
For people who don't know JAX, it can basically it's like AutoGrad for NumPy and Python, right?
Okay. Yeah, and it's you just write normal NumPy code, but actually under the hood it's using some magic XLA so that it goes faster. But yeah, it provides your grad, and then it can take grad through a lot of things. So anyway, just to tell you that you can compute the exact policy gradient, and it's a really cool thing to do when you want to debug your code and understanding and to better understand the properties of your algorithm, because you can always get the true solution. But of course, this is not a substitute for the derivative estimators. Let me just go back to the slides. Because we use these derivative estimators because we don't know the P matrix and the R function, right? Because we're in a model-free setting. So it's not a substitute, but it's good to know, and it's a reminder of where these tools come from. So actor-critic architecture, you need to maintain a Q function on the side, but because you need to learn two things at a time, it creates a bit of instability. And this instability is exactly the same kind that you have in GANs, because the underlying algorithm is basically gradient descent ascent. So you alternate between two types of optimization. So the solution to make actor-critic architectures converge is that you would want, ideally, for the critic, the Q value, to have converged before you can compute your gradient. So you can simulate this by running your by taking more steps of the critic updates than you take steps for the actor updates, which is the policy itself. Or you can set the learning rate for the critic to be higher than the learning rate for the actor. So this is the basic result that Honda showed in his thesis in 2002. And recently, Scott Fujimoto and colleagues really highlighted the importance of doing this in practice. So this was the TD3 paper of Fujimoto and colleagues in 2018. So it makes a big difference. Actor critics can be a bit unstable, but in terms of picture, that looks like this. So we have an actor that outputs actions, goes into the environment, and using the samples of reward, you create an estimate of the value function, the Q of SA. And then using this, you can derive gradient estimates to update your policy. this is the picture depicting actor-critic systems. Now, where I'm going next is to tell you just a few things about temporal abstraction and reinforcement learning, which was the topic that I worked on for many years during my PhD thesis. So temporal abstraction is a form of abstraction where instead of abstracting over the features, we're trying to abstract decisions in time. And intuitively, I like to explain that in terms of like taking the metro, let's say in Montreal, and you take the subway. So what's great about taking the subway when it works and when there's no disease is you just go to the nearest metro station, sit in the metro, and then it brings you to whatever you want. And you don't have to worry about all the messy details of navigating at the surface level. So it just brings you, it just teleports you to the place you want. So it's a form of, I like to think of this as an analogy for temporal abstraction, where you decompose your problem into sub-steps so as to make your life easier. And the idea of decomposing problems into smaller sub-problems has also been studied in many different fields. In optimal control, for example, in this application for the control of a steel manufacturing processing plant, it's been done quite a bunch too in planning, starting from the strips planners in the 70s as well. But in reinforcement learning, we typically model that in the so-called options framework, where a set of options, the options, by the way, have nothing to do with stock options. They're just abstractions that are outputting new actions. And so we have a set of options like this that interacts with the environment. And then once in a while, a policyholder option chooses the next option to follow. And more specifically, what an option is, it's defined as three things. It has an initiation set, for which the semantic is something like, if you have a robot navigation domain, the initiation set would tell you in which subset of the state space you're allowed to use the given option. So for example, if there's no obstacle in front, then you're allowed to pick the policy which drives forward, which is the policy of an option, pi sub O. And then you do that until you reach a termination condition according to beta of O. So for example, that would be like you drive forward until you find a charger. And then once you've met the termination condition, you pick a new option and then you repeat. So in my work, I've been working on learning these options automatically. So the theory for planning with a set of options that is given to you is quite mature, and we understand how that works pretty well. But the biggest problem, and it's still open today, is how to design and how to learn these options automatically. So what I've done in my work during my PhD thesis was to come up with a variant of the actor-critic architecture to learn options. And so the picture looks similar to what we had before, but now we have these options in there. And more importantly, there were some details that had to be taken care of in terms of the Markov chain structure that you have when you deal with options, because the technical reason here is that you no longer have a Markov decision process, but you have a so-called semi-Markov decision process. So you need to take care of that before you go ahead and apply these tools. So we applied that to Atari back then, and we were able to find options. So the systems would learn options on its own that were not specified by us. For example, in that game of Sequest, where it would learn an option that specializes in action sequences going up and action sequences going down, and all of that behavior was not encoded by us. It was found by the system itself. And then same thing here in a game called Breakout, where we're highlighting a strategy that we've developed in a follow-up paper that allows us to come up with more meaningful option. Because the way it's designed, if you just try to optimize for the expected return, there are multiple solutions to that actually. And some of these solutions are not the ones we expect, namely that you can switch from one option to the other at every time step. So the lack of temporal commitment basically is something we don't desire in practice. And so we've incorporated this regularization strategy where this is what we see in the middle picture, where the color coding scheme represents the choice of option in time. So this is to compare with the first picture where there's no such regularization, and such strategy helps quite a bit. So I'm not going to say much more about this, but I just wanted to highlight the fact that there are frameworks to talk about temporal abstraction and hierarchical reinforcement learning. There's been quite a lot of other work after Option Critic, this work over there in 2017. There's been some very interesting work in hierarchical reinforcement learning that are also based on ideas from actor-critic systems. And I encourage you to have a look at these things. But generally speaking, much of hierarchical reinforcement learning in temporal abstraction is still very much open. And I would say that perhaps one reason for this is that I think we still lack a good understanding of what we're trying to do, perhaps. And so very much open, but I encourage you to work on this. I think there are a bunch of important applications that could come out of this. So that leads me to the part on model-based RL. And so in model-based RL, so the algorithms we've seen so far were all model-free. So we were not assuming any knowledge of the matrix P or the reward function, but there's been a lot of interest as well in coming up with methods that are trying to find a model of the world, and that uses that model to plan and to derive better policies. And so model-based RL, I'd say as of now, is not so much of a successful technique compared to the model-free techniques. There are quite some challenges to make it work. But in other fields, especially in optimal control, this has been the dominant paradigm. It's been the dominant paradigm because in these fields, there's a tradition where you would spend a lot of time actually modeling your system by hand, gathering expert knowledge, and really expressing all you know about the domain, which is something we don't want to do usually in reinforcement learning. So there, in optimal control, oftentimes this model-based methodology is combined in the so-called model predictive control framework, where you're using a model to make predictions about the actions you should be taking. But because oftentimes this model is deterministic and it's imperfect, you will quickly realize that the world doesn't function the way that you've modeled it. And so this MPC strategy basically consists in replanning very, very, very fast so that you account for the bad predictions you've been making. So it looks like the typical agent interaction loop of RL, but where the agent box now has a model. And then using this model, we run some sort of optimizer that outputs the next action that the agent thinks it should take according to its model.
The model is also updated as you learn, right?
It depends on which in which setting, but it doesn't have to. So the MPC and the MPC methodology, you would account for the model misspecification by replanning really, really fast. In some cases, depending on the class of solvers you use, you could be re-updating it like 100 times a second, for example.
Okay.
So these MPC controllers are very mature. It's a methodology that is very mature, that works, that has been deployed, that is actually running on spacecrafts. That's how we send rockets to space. That's how we control airplanes. That's how chemical power plants are being controlled. So it's very mature, but of course it relies on prior knowledge to design these models. But once you've got a good model, then the rest, the optimization on top, these tools are very, very mature. It works. So just to introduce quickly what this trajectory optimization methodology consists of. So I talked about MPC, but at the core of MPC is trajectory optimization. Namely, we're trying to, this time we're not so much into trying to find a policy, but we're trying to get a full sequence of actions that we think we should take, and then carry on with these actions. So this is the trajectory optimization problem. And in the simplest case, it's written down as a deterministic problem of the form, which looks like a lot what we've done before, except that now we minimize the cost. And now we're interested in finding the trajectory. This is really where the difference is, right? Our variables now are the full open loop sequence of actions. So an open loop sequence is like, let's say you would decide that you want to do left, right, 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 left, left. Well, you just go ahead and do it irrespective of what the state actually is. And so that's why the problem here is cast in this deterministic form, because we're trying to do trajectory optimization. And so the function f here describes the dynamics of the system. U here is the control. So usually in control theory, we use the letter U instead of A, and C because we work with a cost, and X is a state. So T here, as usual, is the horizon. And then you can view the state x t plus 1 itself as a variable, and U as well. So when you make some assumptions about f, in particular, if you assume that f is linear and that the C is quadratic, that gives you a problem formulation called LQR. And the theory for LQR is very, very rich and very developed, because a lot of the results can be analyzed and in closed form. But of course, that methodology also applies to when n is f per me is nonlinear, and in that case, you treat this problem as a nonlinear program, and then you can throw any nonlinear programming solver, SQP, interior point methods, so on and so forth. Now, what I wanted to share with you is that it's kind of cool to see that, in fact, what we do when you train neural networks is exactly optimal control in discrete time. And the connection here is you would think of, let's say, the layers to make things simple as the function f here, and then the output of the layer as the state. And now that becomes a discrete time optimal control problem. And just to make that more closer to the problem setup, we have usually, instead of having a cost per layer, let's say, we just have a cost at the last layer. And now, if we solve that problem, so this is an equality constraint program. So the typical tool here is to use the Lagrange multiplier. So we write the Lagrangian for this problem. So it's the cost here, and then we add the residual, essentially, of the predictions times the Lagrange multiplier lambda t, and we have one Lagrange multiplier per stage. And from the standard theory in equality constraint programming, if we found a solution to the previous problem, then we know that there must exist a set of Lagrange multipliers such that when you plug your optimal solution in Lagrange multiplier and take the gradient of the Lagrangian, that should be 0. So it's just a generalization of the first order stationary condition of unconstrained optimization, but for the constraint case. So let's pretend we do this, and then we solve for the gradient of the Lagrangian is equal to 0, and then we solve for lambda, and we get these equations here. And these equations are special because they're related to the so-called Pontryagin maximum principle, which is a really fundamental tool in optimal control. What I want to highlight here is that this middle equation over there describes how we adjust, how we update our Lagrange multiplier starting from the last time step. So let's say neural net, the last layer. The Lagrange multiplier turns out to be equivalent to what we call the adjoint variable in reverse mode automatic differentiation. Or, and that equation here, lambda I, the middle one, is how we update our adjoint variable, and it's called the adjoint equation. And this is exactly the computation that backprop would be carrying when you apply backprop in neural net. And then finally, the last expression is just basically combining that adjoint variable and then the chain rule. But at the core of it is the adjoint equation and the adjoint variable. This amounts exactly to the basic principle of backpropagation and reverse mode automatic differentiation. So this connection was actually introduced in supervised learning by Yann Lequin in 1988, but actually the idea was known in other fields. Lequin himself also acknowledges that the connection to discrete time optimal control has been known before. But usually in our field, whenever we talk about the connection to reverse mode AD and Lagrangian, we usually cite Lequin, but actually was used and widely known in other fields, especially in the field of automatic differentiation. This trick, by the way, was leveraged in 2016 by Taylor and colleague to train neural networks without doing the typical backprop procedure, and so by solving this equality constraint program. The same idea also holds in continuous time, but now instead of having a discrete set of states, we now have a continuum, and now we describe the dynamics in terms of a differential equation. So this x dot of t is the time derivative of x. So it describes how the state changes instead. And f can be linear, can be nonlinear. We have also a cost function, but now instead of taking a sum, we have an integral. And that's pretty much it. We're given the initial state, and now we still want to find an optimal sequence of control. But here, the control itself, it's a control function. So that's why it's u of t. It's a control function because t is the timeline. It's real value. So if you basically carry the same exercise and write the continuous analog to the Lagrangian, and then set its derivative to 0, which in that case amounts to applying the calculus of variation, it gives you the so-called Euler-Lagrange equation, which are also the basis for Pontryagin's maximum principle. And these equations are actually, first of all, the form is pretty much like what we have in the discrete case, but now it applies to the continuous case. And what's interesting here is that this trick here, where the lambda dot is once again the adjoint equation, but now in continuous time. Now this is defining a set of differential equations where x is the dynamics of your system, but now you also have a differential equation for the adjoint variable. So how you solve for this usually is that you integrate x forward, then that gives you x state at the last time step, and then you integrate backwards your adjoint equation. And what's cool is that this is actually the basis for the so-called neural ODEs, which has won the Best Paper Award at NeurIPS in 2019. So neural ODEs were about basically learning ODEs that are parameterized by neural net. So where f here would be a neural net. And in order to do that efficiently, to take the gradient through an ODE, they use this principle over there, which amounts to the so-called reverse mode automatic differentiation. So that's really what it is. So the point of this little detour in optimal control was to tell you that, first of all, that there are some really mature tools in trajectory optimization to do model-based planning, especially when combined with MPC methodology, but also that you can use optimal control to understand our optimization methods that we also apply just beyond reinforcement learning, that we apply in supervised learning as well. And so you can think of backprop itself as an application of discrete time optimal control, and also more recently as neural ODEs as a consequence of the Euler-Lagrange equation from continuous time optimal control. And where I'm very interested and excited personally is also at the interplay of optimal control in learning, where instead of using models that are given to us, we, let's say, parameterize f by a neural net and then learn it so that so that we get better performance. So to combine the advantages of learning methods with deep neural networks with the very mature techniques from optimal control, which, by the way, one of the advantages of optimal control is that it's very natural and easy to add constraints, which can be very useful if you have robustness or safety constraints, something that would be quite challenging otherwise to do in with the typical sets of model-free methods in reinforcement learning. So to say a few more things regarding models, and this is a bit more in the typical Markov decision process framework. There's, I think, a lot of interest and there's been some really interesting ongoing work on learning models. And I would say that this is very the challenge right now is to learn good models for reinforcement learning. There's been some early attempts, let's say in the Atari domain, to learn models. But what has been quickly found is that even with the best model, the slightest error that you make really quickly compounds in the Bellman optimality equations. and then quickly your planner gets off track, and then there's nothing to do with this. So far, we haven't really gotten good results with model-based RL. That being said, there's been this recent result by DeepMind with their mu0 architecture, which shows a lot of promise in better dealing with model-based RL. But I'm personally interested in that question as well. And the approach and the bet that I'm making is that we need to be learning models that are better suited for planning, that are basically coupled with the goal of getting good policies out of them. And this is in contrast with the direct methodology in which you would, let's say, try to estimate the transition matrix or reward function by simply gathering data and doing MLE estimation out of your data. So that methodology has been attempted quite a bit, but it shows some weaknesses, especially in higher dimensional spaces, for the reason that I mentioned, that sometimes we might be trying to allocate some representational power to model parts of the environments that are not relevant for the thing that we care about, which is to get good policies. So the line of work here that I think is very interesting and I'm pursuing with my group is inspired by the seminal work of Rust in 1988. So Rust is a researcher that comes from econometrics. So it's not someone from RL, but his work is very, very neat, and it's been a precursor to many things in reinforcement learning. So in this 1988 paper, it's called Structural Estimation of Markov Decision Processes, what Rust was interested to do was to infer an MDP model that would be able to model the behavior of a car mechanics or someone who is fixing buses, actually, and in order to better understand his thought process, essentially. So they had access to data, and they wanted to find a reward function in transition matrix such that when you would plan with it, you would get a distribution of actions and states that matches the data you've got in terms of log likelihood. So you can view that in terms of, like, let's say, a computation graph that takes the model parameters, does planning to get a Q function, derives an optimal policy out of Q, and then compute the log likelihood out of the data set. And now what Rust was doing was essentially optimize that thing end to end, which is pretty cool when you think about it from the point of view of end-to-end learning these days. But why this is difficult to do is that mapping from policy parameters to optimal policy goes through essentially a fixed point problem. So you need to be able to take a gradient through a fixed point equation. So if you want to think in terms of it as a neural net, it's as if, let's say, you have an infinite number of layers. So like an infinite RNN in a way, where each layer is an application of the Bellman optimality operator. So how would you do that tractively, you know? So the trick here in Rust, and this has been used by Rust without actually mentioning it this way, is to use what we call in machine learning implicit differentiation, where implicit differentiation is a technique based on the implicit function theorem that allows us to get some the gradient that basically tells us how is my fixed point going to change as I change my parameters, and allows us to do that without having to remember anything about the algorithm, about the process that led us to that solution. So in other words, we don't need to remember all the variables the way we'd have to, let's say, in backpropagation through time. So that's what Rust did. Now in RL, in the 90s, we then saw the first proposal to do inverse RL. And inverse RL, inverse reinforcement learning, is essentially based on Rust's structural estimation problem. It's been acknowledged, but perhaps not known well enough in our community. So inverse RL is the problem of finding a reward function from data. The problem setting of Rust is even more general in that you can also estimate even a transition function indirectly from demonstration. The same idea of doing inferring, let's say, a model from demonstration has also been the basis for the differentiable MPC work of Brandon Namos in 2018. And the trick at play here is also implicit differentiation, but applied to the stationary condition of the Lagrangian. Now, same idea has also been pursued by Jonathan Sorg and Sitinder in 2010 in their so-called optimal reward design problem. So optimal reward design, what they're trying to do here is to find a parameters of a reward function, a synthetic reward function, such that when they plan with it, derive a policy, then they get good performance. So it's the same computation graph up there, but instead of the log livelihood, it's the expected return. So it means that the last part of the pipeline here would involve a policy gradient estimator, and then the rest would involve some sort of implicit differentiation approach. But back then, Sorg and Sitinger used the paper by Geger-Lee-Ner and Chaba-Shivas-Pari on imitation learning, which was an attempt to basically provide some conditions under which the gradient through the fixed point exists. And they had to do a bit of math to make sure that, to prove that this result holds. The reason why they had to go through this effort was actually that they use the, let's call it the hard Bellman optimality operator. The problem with this is the hard Bellman optimality operator is non-differentiable. It's a max. Whereas Rust in 88 got around this by using a smooth Bellman operator. So everything was end-to-end differentiable. Whereas the Ner Shibashvili had to use notions of subgradients and things like this. So the Sorg paper was based on Ner, which the Ner paper can be seen as an application of the implicit function theorem, with the exception that it's not truly differentiable because they don't use the smooth Bellman operator. Now, you don't really need to do model-based planning in that part of the pipeline. You could also do model-free. You could do policy gradient methods. There are a bunch of different choices. So it's a very general template. And the reason why I think this is really cool is that I think many of us in reinforcement learning have the intuition that the models that we need to build need to be just centered on the agent. They just need to reflect the needs of the agent for representing the world, and that representation ought to be subjective, to use a bit of a philosophical term here, in that sense that we just want our agents to model whatever they need to solve the task at hand. And in that framework, we're really kind of blending model-based and model-free. The distinction becomes quite fuzzy at this point. So I think this is a pretty important line of work that we should pursue, because model-based has a lot of potential but hasn't been leveraged very much. And I think there are lots of great tools that we could also use from optimal control. And the interplay of optimal control and reinforcement learning is something that many of us are interested in. In fact, we now have a new conference even called Learning for Dynamics and Control, which gathers people from optimal control and learning together. And I think we have a lot to learn from both sides, in the same way that I think we have a lot to learn as well from the simulation community. Just a little parenthesis here, this is my last slide, but what we call the reparameterization trick in machine learning, which is fairly recent, is a tool that has been used for a long time in the simulation community. And in that community, it's known as the infinitesimal perturbation analysis trick. And so there are a bunch of theorems, characterizations, and results available for IPA that could inform us of the properties of reparameterization, which is very hot nowadays. So lots of things to learn as well from simulation community. So please talk to your colleagues in the OR department. I think you can learn a lot from them. They can learn a lot from you, and together we can come up with better solutions. So in general, my problem has to do with learning over a long horizon. So this is my bias, of course, here. So I think that learning over a long horizon is a key challenge across disciplines, even reinforcement learning, supervised learning. And I think there's lots of great ideas to take from from the constraint perspective on trajectory optimization, in which we basically decouple our problem into sub-problems using these equality constraints. And that may help us in fighting the vanishing gradient problem. So these are things that we're actively pursuing in my lab. Generally speaking, the problem of representation learning is very much open. Despite the success of DQM and in the Atari games, we still have representations that are very brittle, that don't allow us to deal well with changes in the environment, with different tasks in a multitask regime or in a continual learning regime. And this is probably a problem of representation. So although we have deep learning, representation learning is still very much open. How do you get a good representation that allows your agent to learn fast and efficiently across the multiple environments and across the changing world? So model-based RL, this is what we just discussed. How can we build good models that lead to good policies, that are well adapted, that are robust? I think this is both interesting in the discrete time case as well as in the continuous time case. Now that we've made the step and we're willing to work with ODEs now in neural networks thanks to neural ODEs, this opens the way to lots of new applications in which we use a model beyond the MDP framework, and where, let's say, we model the world by an ODE. And this is very relevant, especially these days in the context of modeling diseases and the spread of diseases, where it's common to model these things in terms of ODEs. But where, of course, here our contribution from the learning side is actually to come up with good methods for finding these models, learning these models from data, aka the system identification problem. And finally, the class of methods from model-free reinforcement learning, things like temporal difference learning, they're very elegant because of their time complexity and memory. There's some, but the problem is tend to be quite simple and efficient, require a lot of data. So depending on in which setting you're working on there, if you're someone who's working with a small amount of data in healthcare application, this might be an issue. If you're designing algorithm with AGI in mind, that may not be an issue. So it depends a bit on what are your goals, but sample efficiency is definitely something that we got to keep in mind. And in that sense, there might be value as well in combining prior knowledge. If you're working in problem setting where you have expert knowledge about either the structure of your solution, the structure of your model, these things can be incorporated and then combined also with learning. We've got some good example from Yi-Song Yu at Caltech, especially on combining ODEs with a known functional form describing the mechanics of their quadcopters with learning methods to learn residual models, for example. So this is very promising work as well. And finally, I think to come up with better and robust and safe RL, there might be tools to leverage in optimal control. It's a very natural setting for expressing constraints. It can be just added literally to our NLP, to our nonlinear program, and then we can get hard constraints and safety guarantees on our solution, which is something we wouldn't be able to do easily with more traditional temporal difference learning or policy gradient-based methods. So with that, I think it concludes the tutorial. I'd be glad to take more questions if you have any. And if there's a takeaway here is that reinforcement learning is very multidisciplinary. It's important to understand the motivations behind what people are doing in their respective field, and to respect also their point of view on this, and to really realize that they come with different objectives, and then it shapes the kind of tools that they use. But overall, we have to gain from using as much and to talk to each other. Thank you.
Thank you very much, Pierre-Luc. It was a very interesting and very clear talk. I appreciate your multidisciplinary perspective on this material. Really interesting. I have a raised hand here from Chris Drummond, who would like to ask a question. So I'm going to try to unmute you, Chris. Can you go ahead?
Okay, I think I've succeeded. It seems to me that a lot of the problems in reinforcement learning are early in the process. So particularly if you have a very sparse reward, it takes you a long time to even discover the reward initially. But once you start to have some sort of policy, the process is faster. So that makes me think that the model I want is not a model that I want to use, but I'd like a model for the early on in the process. And then I'm happy to discard the model. Once I know enough, then I would be happy to discard it. So it'd be interesting to talk about using a model as a bootstrapping method to get somewhere and then discarding it.
So this is not something I've thought about, but you're right that dealing with sparse reward is something very challenging in reinforcement learning. And as far as I know, we don't have a good theoretical grip on what it even means to have sparse rewards, but we know very well in practice what it means. Let's say you only got a 0 or 1 at the end of your trajectory, and that tends to be really hard to learn over. In a sense, the eligibility traces mechanism is a very basic mechanism to do credit assignment using the recency heuristic. But I believe that there is much more to be done at the intersection of causal learning, in particular, in credit assignment in the context of reinforcement learning. Recency heuristic can be seen as a very simple heuristic for causal reasoning. So I think there's more to gain here. Regarding the discarding the model, I'm not too sure I have an opinion with this, but there are definitely some elements that intersects well with ideas like DINA, in which we combine both experience from the real world in a model-free fashion, and we combine that with prediction from our model. But the discarding, that would be something I'd have to think a bit more as to where it fits, but I think you're raising a good point here.
Any other questions, Chris?
Well, I mean, just to say, yeah, the reason for discarding it was to be able to live with imperfect models. So what you said earlier on was if you have a model that's not perfect, that at some point in time, it's more dangerous than it's helpful. But I think often the way people have a model, a rough model of how things work, and in controllers, in terms of controllers, if you could start with a linear model, for instance, even though you didn't expect that the optimal model would be linear.
Yeah, so the problem of models mystification is very, very real. I think the interesting lesson from MPC is that even though their models might not be perfect, by virtue of replanning really fast, you can still account for a model imperfection. There's some great results by Byron Boots and colleagues on drawing connection between MPC and online learning. And they've also have great experimental results showing MPC with neural networks on actual self-driving cars that are able to drive, across really tough, rough terrains and adjust to the on-model disturbances really quickly by virtue of replanning, solving their QPs really fast. But you're right. If you apply, if we just learn a model naively from an MLE model, then plan with it, there's that compounding error that might quickly occur, and then it might do more harm than good. So having a fallback mechanism, such as what you're proposing, might be important.
Good, thank you.
Does anybody else have any questions? I might have an easy one for you. You mentioned that you're specifically interested in problems where you have to make decisions over very long time spans. I'm just wondering, are there specific problems that are like representative of that challenge for you?
That's a problem that occurs quite fast. The long horizon, you don't need much to encounter the problem. It relates also very much to the credit assignment problem, where you have sparse rewards, where sparse reward problems are quite common. It's much easier to represent a task, to express a task in terms of whether you succeeded or not, than to craft like a reward function that assigns credit over each individual time step. So these two things are really intertwined with each other, like sparse rewards and credit assignment over long horizons.
Does anybody else have any questions? Well, in that case, I think I will thank our speaker again for taking the time, preparing the materials. I have put up the link to the Colab notebook on the Slack channel, and we will be putting it on the web page for the program of the conference, I believe. Also, Pierre-Luc says the materials on his website are also good resources for people who want to get into this stuff. So that's it. Thanks a lot, Pierre-Luc.
Thank you.
Yes, thank you, Gabriel, for chairing the session, and thanks a lot, Pierre-Luc, for giving a very nice tutorial this afternoon. And the tutorial will be available as a replay on the YouTube channel for people who may have missed it. So,
great.
Thank you.